Hello everyone, it's April 27th. Finished the committee meeting, did pretty well. And I think my committee members also like it, as always. That's a good thing, but we still have a lot of other things to do. So today the goal is, of course, we're going to try to finish the challenge, but depending on how much time we have after the challenge, we can decide how much more we want to go into that hard problem. But anyway, let's go for the challenge first. Smallest string with swaps seems to be a new problem. No, it's not. And oh, look at this. So it's a tough one. Look at this. 2019 was a long time ago. I tried to solve. Why did I solve it in the first place? It's like 1,000 something. Maybe that's the one of the contest. No, that's not right. That's 9 a.m. in the morning. And I tried. Didn't work. Did I really solve it for 6 hours? No, I think I tried it again later on, and finally got it to work. And then next day, I think I improved it. All right, so it seems to be a tough one. But let's see. You're given a string S and an array of pairs of indices in the string pairs, where pairs I equals AB indicate two indices of the string. You can swap the characters at any pair of indices in the given pair any number of times. Return the lexicographically smallest string that S can be changed to after using the swaps. So what we're saying is these are the two indices that we can swap. So we can swap the characters at any pair of indices in the given pairs any number of times. And we return the smallest string after. Very interesting problem. So in this case, swap 0 and 3. 0, 1, 2, 3, and then swap 1 and 2. So it will be B, C, A, B, A, C, D. And look at this. We have 0. It's kind of shared by 2. So when we swap 0, 3, and we can swap 0, 2. So that can we can bring so 0, 3 and then 0, 2. We bring B here, and then we swap 1, 2. Wow, okay. How are we going to do that? I have no clue at all. Damn. Alright, calm down. So, we want to swap, right? So each pair we're going to swap. The next pair we're going to swap. What does swap do? Swap just... we put one letter to the front, one on to the end. And if we swap again, hold on. Let's check the first example, right? So we have DCAB. Let's say the swap. We kind of had a feeling that we're in the graph, so let's use the graph. So 0 is 3, so it's D, 0, 1, 2, so D and B, we say D and B are linked. And then 1, 2, A and C are linked. And that's it. So what we are saying is, if we have this graph, we want to find within this graph. Are we saying within the graph we can swap all the nodes? Well, yeah. I think that means within this graph, we can swap all the nodes within this graph. So the first problem, we have two separate graphs. So the first graph, we can try to find the smallest. So that's DB, right? We can change to B and D. And then in the second graph, we're going to change to A and C. So now we want to put them together. How do we put them together? So we know the indices, right? So we know their indices. So they can be any indices. So we say the indices is 0 and 3, and this is 1 and 2. So we say 0 is going to be B, 1 and be A, 2 and be C, and 3 and B. So B, A, C, D. Okay? So second one, we have D goes to B, right? C goes to A, and then D goes to A. So D goes to A. So now we have D, B, A, C. That's how the graph is. So this means everybody is inside this chain in the graph. And because we can swap any pair, right? We can swap any pair. If they're inside the graph, we can prove that we can make any type of order, right? How do we prove that? Well, we say because they're all connected, right? They're all connected. So like just means they're connected. So if they're connected, if we want to swap some and they're connected to some others, right? So we can always, you know, like if they connect to the same one, then we can always swap however we want, right? We can swap here and then we can swap, right? So what if they're not connecting together? If they're not connecting together, then but they're inside the same graph, that means there will be something, right? That's connecting. So we can kind of extend this idea, right? So let's say within this three, we can change to come here and come here. Yeah. So we can say that once you're inside the same graph, you can always produce any type of order you want. So this problem becomes we are going to go through the whole thing, and we want to know, let's say which indices are connected to which indices instead of which the letter itself, because that can kind of tell us afterwards how to put things together, right? So we say indices connected, so all these indices are connected, right? Okay. And then we have the other indices are connected. And then we go into the string, bring those indices out, right? And we sorted it, right? So that's the order. And then after sorted it, then that's how those indices will look like, right? That's how the indices are. We can sort the index as well and sort the values. So then we're going to put them together. Okay, so we have a solution. And I'm pretty sure that's how it's done. Let's give this a shot. Honestly, I actually have some memory of this, even though that's like more than 2 years ago. I have, not more than 2 years, about 2 years ago. I have memory. All right, here's how it's gonna happen. So what we're gonna first do is try to find which ones are in the indices. How do we do that? Union find. I mean, seriously, this is union find. You gotta be kidding me. This is union find. We use union find, we can find the oh Lord. Really? Are we saying union find? You gotta be kidding me. Can we not use union find? We have a pair, right? And then we find a new one, and then we find this. Now how do you union those together? Ah, screw you. I still cannot write union find all by myself. What else I need? No, I think this is parent. Rank, isn't that just whatever? Nope. Find is to find your parent, right? And we say So I can find your parent, okay? So it's actually the grandparent. And then we say if these two are the same, then if these two are not the same, then is that right? Yeah, if I find the parent of parent is the same, then we're good. If they're not the same, right? So like, and then we set this to, hold on, maybe that's, I'm gonna try. I can say parent equals self.find self.parent v, okay? And then after doing that, so if parent is not equal to self.parent v, and then no, I can't. I forgot. If self.parent is not the same, all right, so what does it mean? It means if self.parent, so my parent, if my parent is not equal to myself, is that what it says? If my parent is not equal to myself, then, wait, hold on. If it's not equal to myself, then I need to find. So the initial, what we're saying is, I am my own group, right? That's what we say, I am my own group. So this just say I am not my own group, then we say self.parent v. Then my parent, we need to find it again, right? So that's means self.find self.parent v. So we will find my parent's parent. Right, and after that, I'm going to return self.parent, my parent. Okay? So this basically just saying if it's the same, then I am the root already. So I just return it. Perfect. If I am not, right? If my parent is not me, then it means I must got here through some sort of union before. So I need to kind of find a compress. It's a compress the path again. All right, union will be say x and y. Oh, that's why I use x. Gotcha. Right, x and y, and this will return a Boolean value. And then we say px py equals self.find x and self.find y. Right. If they're the same, if px is not equal to py, if they're not the same, then what? Then we say so the parents are not the same. So one of the parents need to belong to the others, right? So we say rank. Whoever has a higher rank. Then we say if self dot rank on whom? Whose rank? Should be the parents' rank, right? It's the parents' rank. Yes. And we start from 0. Rank will start from 0. Okay? So it's parents' rank. So we say if the px rank is larger than py is parent of y's rank. If that's the case, then we say we take a higher rank. Yeah, we take higher rank. So if that's the case, then we say self.parent py shall equal to px. So elif self.rank px is smaller than self.rank py. Right, if it's smaller, then we say self.parent then px, because the parent equals py. Right, we just make them all equal to py. Else, now this is the rank are the same. If the two has the same rank, then we randomly pick one. Then we just, let's say we randomly pick px. Right, after picking px, we say self.rank px, because we pick it, so it means this one has to be larger. And then return true. We did union. Otherwise, return false. Okay. So uf equals dsu. Should be line s. Okay. Now what? Now we have to go through this. For each pair, we do union and find, right? So when you say for A and B in pairs, right? And then we just UF union A and B. Okay. So once we finish that, then we have to basically look into the rank. No, look into the parent, right? So look into the parent. We need to find out how many different groups do we have. Now, how do we do that? So we have to loop through parent, right? And then let's use a dictionary. Okay. So we say groups. No, G's graphs. So it can be this, right? Now we just say for I and P in enumerate UF dot parent, right? Then look in default dict. Okay, default dict of a list. Right, so we say from collections import default dict, and then we say gs a p, right, dot append I. So eventually, by doing this, we get all the p's and we have all the i's, and then what? And then res, let's say, equal to times n, okay? And then I don't care about the keys, we care about the value. So I'm going to say for a v, right, in gs.values. So each v is a list of values, and we want to first sort them, right? We need to sort them, so we can say v.sort. Okay, this is necessary. Oh, wait, hold on. Is this necessary? Yeah, it's necessary because we will also sort the actual values. And then we're going to say temp will equal to for I in v si, right? And then we're going to sort this one as well. Okay, so temp is sorted. And then we can say so this is a temp, right? Then we just say for I and t in zip it v and temp, right? So we zip it and then we say res I is equal to t, and then we'll fill it up. Once we're done, we're going to return is the join. Let's see if this is right. This is good because it practices, right? BACD practices graph. Practices union find. At least it forces me to at least try to write union find by myself, which is always going to be tough. But it's necessary because in reality, if you're in an interview, you tell the interviewer, I think we can use union find to do this. Okay, implement it. And you're like, can I check how to implement union find? They'll be like, no. And then if you don't do union find, this is not going to be easy to do. So you do have to use union find. Oh, what the hell? We failed on the second one. Doesn't matter. Let's just take a look. Let's take a look at uf.parent. Ooh, what the hell? Oh, we need to do. Wait, we need to do one more round. Yeah, I think we need to do one more round. Unfortunately, just say for I in range n. When is a uf.find? Alright, we're gonna do one more round find. Now, because this one we have to change this. Yep, I don't have other ways. Alright. Disjoint. Disjoint? What is set union? Disjoint set union, and that's what it stands for. Wow, it's exactly the same performance. Slightly faster. Alright, so DSU. We have a rank, we have a parent, right? And then this is actually a path compression. So what does the find do? The find is trying to find my parent. So I check if my parent is myself. It is myself, then there's nothing we need to do, which means I am already the root of this group. If it's not, that means I must come in through some type of union. So basically because of this, let's just compress the path. By compress the path, I'll find my parent's parent, right? And I'll assign that to myself. And then I'll return my parent. Yeah, now that I look at the find, it doesn't make sense. Union, so we try to find both their parents. And the parents is the same, then they're already union, so we just return false. Otherwise, we can we say they have different parents, right? If they have different parents, now we want to union them. So we check the ranking. So this one allows us to decide which parent to use. So we use the parent with higher ranking. So if the PX ranking is higher, use PX. PY ranking is higher, use PY. If both are the same, we arbitrarily pick one. So we say we pick PX. And after that, we increase PX's ranking. I think this is the same as here. If this, we use Y, if this, we use X, we pick X. Yes, exactly the same. So we need to memorize how this one's done. I'm pretty sure that's the solution back then. And other than this, I don't really know what other methods can be used here. Hold on, let me just write today. Let's about this problem. I don't remember why I used this. Is it because I was looking for union find, or I don't remember. 1202. I solved this problem 2 years ago, but I don't remember why I did it. Anyway, I do remember using union find to solve this problem, because we can convert the letter swapping to forming an edge between two indices. So this and another insight, right, is that once several indices are combined, right, combined into one graph, then we can achieve. Then we can make any letter within this graph appear anywhere. This means all we need to do is to find the graphs contained and the graphs described, right, by the pairs. Right? That's all we need to do. We find the graphs, and within each graph, we can easily sort the letters. This is O pairs log n, OM log n, and this is ON. This is O n, and this is ON log n. So what do we call it? ON log n? Yeah, we call it ON log n then. Wait, hold on. Did you? Yeah, just regular solution. Alright, this is the previous one that I used. That's union find. What the hell is this? Subset. Find. Union. It is union find. Huh. Sort reverse. Oh, look at this. For each one, I parent dict. I know this one again. This one again in GS. I see. And then I get it. That's a similar idea. I just realized I don't have the sort here. What we need is to sort this, all right? Hold on, we do need to sort. Yeah, I like this one better. So instead of do I, what we're going to do is S I. Okay, and there's the result. And then what do we do? What we do is we will go from each v and so each I'll look for its parent and I'm gonna pop. Okay. So we do this, and then for G, now for G and GS dot values, G dot sort, reverse equals true, right? And then we can just say for I in range n, right? Then we can say uf.find I, which will give us the parent, and we say gs. What does G stands for? Groups, right? So groups this parent, and then dot pop, that's the smallest, and then we can just say that, right? And then we return dot join this entire thing. Okay. Yep, it's correct as well. Yeah, very good. Did I fail? So and then check the results on this one. Holy moly! I did solve it by myself. Island. Wow, I was pretty good. I don't think I've ever able to do this. Oh my! I hardcore solved it. Screw this. Now the only thing I remember is using the union find. The union find is nice. Let's put this one in it as well. Yeah, I don't think it's going to be any faster though. Oh, wow, I was just saying it's not going to be any faster. This is much faster. So yeah, we remove one level of sorting. Of course it's faster. Alright, so I don't think I want to do the other one, so let's just read the solution and call it a day. Oh, we can use DFS. with DFS, basically, so from this one, we'll try to see how many we can reach, right? Basically, that's how many different things we can reach. Yeah, so basically just we can use DFS to find, we use DFS to find all the connected nodes. So we do this, we go here, let's go here, we try not to go back, and then go. Right, we go through everything. And if they're connected, then we'll definitely visit them. So use DFS to find all the connected nodes, and they will be placed inside the same bucket. We find the other one, and if there's anything that has not been visited, we will try to find that as well. Okay. Yeah, we can use DFS. Yeah, we can use DFS to find the graphs, right? The disjoint graphs. For each list, if it has not been visited, we'll perform DFS and store the vertices and the characters of these indices in a list. Each list represents a different component, and we'll sort each list. Maybe that's the method I used. Yes. Okay, so that's that. And of course, we can do DSU. Oh man, union find is just so good. So good. We just say union and problem solved. Union find. This is also a compression. Look at that. We say if it's larger or equal to, we do this in rank. Okay. I mean, yeah. Just to make one of the rank goes higher. It doesn't really matter. Oh, vertices log vertices, and union find is this complexity. O alpha v. Alpha is the inverse Ackermann function. Iterating over each vertices and perform the find operation. Well, if you know, right? If you know. It's good. People are learning union find. I always love union find. All right, so yeah, that shall be it. And I don't want to do another one. So let's end it right here. Yeah, let's end it right here. I will see you guys tomorrow. Adios.